This lesson comes out of section 1.4, using limits to find tangents. Now in some ways we've already done this, even though it's new section 1.4. In 1.2 and 3 we've done a little bit of finding the slope of a tangent line, and we've even started to do some limits. So we're going to kind of put it all together here a little bit. Let's start with a picture of any function y equals f of x. It could be a polynomial, a quadratic, whatever you want, just a generic graph looking like this. And we're interested at this point P. So I'll call it point P, and we'll call the x-coordinate of that A. So that means the coordinate here is going to be A, comma, f at A. Since I don't know what the function is, I'll just keep it as generic as that. What we've seen that we've done before is we said, well, let's take another point Q. It's a little ways down the road here. And as we move that point Q closer to P, we'll eventually go from having the slope of a secant line to the slope of a tangent line if we can make the point Q infinitely close to P. So let's call this x coordinate. So this is now x comma f at x. So the slope from P to Q, the slope of that little secant line there, is just going to be rise over run, which, as we know, is change in y coordinates over change in x coordinates. So f at x minus f at a divided by x minus a. And so if we then are moving Q so that it's infinitely close to P, we can write it this way, to say the limit as x approaches A, infinitely close, of f at x minus f at a over x minus a. That is actually now the slope of our tangent line. And that will be, I believe your book calls it equation 1. The second equation that also works for this basically starts with the exact same type of picture, just some numeric function, whatever you want to make it look like. We've got point P and we've got point Q. But in this case, they've decided to call, they still start off with this one being called A. So A and f at A. A is the point, the x value where we're looking to find the tangent line. Q, instead of calling it some new variable, they say, well, it's just a tiny bit up the road here, so we'll call it A plus H. So the x-coordinate is A plus H, and the y-coordinate is f of A plus H. Now, seems kind of weird to do that, but when we do the rise over run, the slope of PQ, it's going to be f of A plus H minus f at A divided by A plus H minus A, which actually makes the denominator simplify quite nicely down to an H. So the equation 2 that they're referring to in your book when they're saying the slope of the tangent is to say, well, what's the limit as H approaches 0, in other words, the distance between P and Q approaches 0, of f at A plus H minus f at A over H. And what you find is that these are both useful in certain situations, and in fact can both find you the answer to the slope of a tangent line at a given point. I personally use the second one more often because I find it easier to cancel out the H than to cancel out the x minus a term in the denominator, but I'll show you what I mean by that with an example here in the next example. Since this one's already getting close to 4 minutes, we'll do a separate one.